Howdy! Welcome to Aspire Mountain Academy. I'm Professor Curtis, your instructor for this course in Introductory Statistics. In less than 10 minutes, this video provides practice in conducting goodness of fit hypothesis testing using the old school calculation method. Let's get started. So, to illustrate how to calculate goodness of fit hypothesis testing old school style, we're going to look at this problem where we've got the last digits of weights of 100 randomly selected adults. And we want to test the claim that the sample is from a population of weights in which the last digits occur with the same frequency. So in other words, we want to test the claim that the last digits of the population weights fits a uniform distribution. That's what a uniform distribution is, as all the categories have the same frequency. First, let's check to make sure our requirements are met, because our procedure is built on certain assumptions. So first, the data have been randomly selected. So we've got that. Second, the sample data consists of frequency counts for each of the different categories. So we've got the second one checked off. Third, we have 100 sample values distributed among 10 categories. And those 10 categories are claimed to be equally likely. So the expected frequency for each category is 10, and 10 is greater than 5, so we've met the third requirement. So our requirements have been met. Let's go ahead and form our hypotheses. Remember, for goodness of fit, your null and alternative hypotheses are pretty much set, okay? But you can go through the same process we've been through before. Think of a claim being made, okay? Each of the possible outcomes for the last digit are equally likely to occur. So all those probabilities are going to be, all those proportions are going to be the same because they're equally likely to occur. Remember, the null hypothesis is by definition a statement of equality, so we just list that out. And then typically the alternative hypothesis will reflect the claim, but here, okay, the alternative hypothesis is always going to be the same. It's going to complement the null hypothesis because, that's what the claim is, right? Or claim is that they match up. Well, that's statement of equality, which belongs with the null hypothesis by definition. So we're going to say at least one of those is different. Actually, at least one problem. Let's just say at least one proportion is different. So yeah, at least one of them is different from the rest. Note that we've got, a mismatch here, but that's okay. By definition, goodness of fit testing has, a one-tailed test on the right. Our claim is that the population of last digits fits a uniform distribution. So to get our hypothesis test out, we first got to calculate our test statistic. Doing this the old school way, we typically run through a table. And so what we do is we set up columns for each of the different categories. So one column for each of the last digits. And then we have frequencies of how often we've observed each of those last digits there in our data set. Now what we do is we calculate the expected frequency, which we did previously when we were checking our requirements. Everything is going to be 10 because there's 100 counts total and there's 10 categories. Everything's the same, so we just take 100 divided by 10, and that gives us the 10 for an expected frequency. Next, we subtract the expected from the observed. So in the first category for the 0, we've got 46 minus 10, which gives us 36. In the next column for the 1, we've got 1 minus 10, which gives us negative 9. Then 2 minus 10, which gives us negative 8, so on and so forth. Then what we want to do is we want to take those differences and we want to square them. So we're going to take 36 and we're going to square it. That gives us 1296. Negative 9 squared is 81. Negative 8 squared is 64, so on and so forth. Now we're going to take each of those squares and we're going to divide by the expected frequency. So 1296 divided by 10 gives us 129.6. 81 divided by 10 gives us 8.1, so on and so forth for the remaining categories. Then we're going to take all of those numbers and add them together because that's going to give us our test statistic. So we sum all those numbers together there, and that gives us 212.8. This then is our test statistic. Now we've got our test statistic, we can conclude our hypothesis test. We use the test statistic to find a p-value. So in our chi-square calculator, or if you want to go truly old school, pull out your chi-square distribution table. Either way, we've got 10 categories, so that's 9 degrees of freedom. We put in the test statistic, and it's a right-tailed test. You're not seeing it there in the graphic there in the calculator, but, 212 is really off to the right, so it's a really small p-value that we get out is practically 0. Again, there's our test statistic we put in. The p-value is what comes out. With a p-value of 0, we're definitely less than 5% significance level, so we're inside the region of rejection. We reject the null hypothesis. Alternatively, we can compare the test statistic with the critical value. We get a critical value by putting in, again, 9 degrees of freedom, 5% significance level there for the alpha, and then our critical value is what comes out there, the horizontal value. So that red region is our critical region bounded by the critical value. There on the left, 16.9. So alpha goes in there, critical value comes out here, and we can compare the test statistic with the critical value. 212 is a whole lot bigger than 16.9. So we're well to the right of our critical value, well within that right tail of our distribution. Therefore, we're in the region of rejection. We reject the null hypothesis. Either way, we get the same conclusion, reject the null hypothesis. And of course, when we reject the null hypothesis, there's always sufficient evidence. And that's what we, to interpret the result, we're going to actually recall what our null hypothesis is. Rejected the null hypothesis. What did the null hypothesis say? The null hypothesis said everything was the same. We rejected that. So what does that mean? That means the statement is false. And what makes this statement false? One of these proportions is obviously not the same as the others. Like that old song from Sesame Street. One of these things is not like the other. One of these things is not quite the same. So, one of these, last digits, is occurring at a different frequency than the others. It could be 1, it could be 2, it could be 3, we don't know. All the test is telling us is that at least one of them is different. That's all the test is telling us. So we can conclude that the sample does not come from a population that has a uniform distribution. They don't match up because at least one of those proportions is different. Or in stats parlance, we have sufficient evidence to support the claim that the sample data does not come from a population that fits a uniform distribution. But hey, however you word it, it's the same thing. And that brings us to the end of this mini lecture. I hope you found it helpful. You can find more mini lectures for this and other courses at AspireMountainAcademy.com. Thanks for watching. I'll see you in the next video.